thanks, Matthias, and thanks for organizer. It's a real pleasure to meet all my old old friends and the young friends too. And I'm going to talk. It's really a new talk. It's a joint work with Jalal Fadili from France, and I'm going to talk about a method which is very interesting and which is not well known in the optimization community, which is the Ravine method. So our first objective was to study this method, to compare it with the Nesterov method. And in the process, we discovered many new and I think interesting results. And most important, at the end of our lecture, we are going to present new algorithms, which I think are better than the original historical algorithms. Right, so let's first present the Ravine accelerated gradient method. It was introduced, the whole method, it was introduced by Gelfand and Tseltin in 1961. Gelfand is the well-known Russian mathematician, you see, who wrote in many fields of mathematics, especially in functional analysis. So the Ravine method, here I use a capital R, but it's a common word. You see, Ravine is just the Ravine. It mimics the flow of water in the mountains. You see, here you have small ravines, okay, which are small steep ravines, and the water goes down through these small steep ravines. And in the bottom of the mountain, you have the valley, you see, and which recollects the water from the small ravines. Here you have one ravine, a second ravine, a third ravine, fourth ravine, which are in thin blue, and in thick blue you have the main river, which collects the ravine. This was the mechanical intuition behind the Ravine method. So if you want to translate this from a mathematical point of view, here you have a ravine. So here we just take a very simple model. It's just a gradient step. You have a gradient step for each ravine. So here you have two ravines. So for each of them, you compute a gradient. And then you recollect the water from the two ravines in the bottom of a valley through this extrapolation scheme. So from a mathematical point of view, we take S a fixed gradient step. For simplicity, you can make it vary, you see, if you want. But the important point is the extrapolation. See, you know that for inertial method, this is inertial method. The extrapolation is a decisive feature. In the historical version of Ravine method, the extrapolation is fixed. And in modern algorithmic method, you know that taking the extrapolation of this form, 1 minus alpha over k, where alpha is greater or equal than 3, is very interesting. It makes acceleration, and it's directly linked with the Nesterov accelerated gradient. Right, so here is the geometrical view of the algorithm. You have the two ravines. You see, for a ravine, in order to distinguish the method from the Nesterov, I use the variable y for ravine. We should use variable x for Nesterov. You will understand in a moment. So here are the two ravines. So here two gradient steps, and then you recollect them by extrapolation. If this is the bottom of the valley, and you pass from yk minus 1 yk to yk plus 1. Y index k plus 1. So it's an inertial method. Right. So I discovered this method rather recently. It was at the occasion of the workshop in variational analysis in Lecce, Italy. It was a lecture by Polyak, who gave a survey lecture on the inertial method in optimization. And he mentioned the Ravine method. For me, it was a real surprise at the intuition that this was an interesting method. And in fact, the Ravine method is really the precursor of the accelerated gradient method. It has long been ignored, and it's at the forefront of current research. That's what I'm going to explain in a moment. And according to Suritsra, he also gave a recent survey lecture on the optimization for machine learning and accelerated gradient at MIT. He said this sentence, I think, very good sentence. Ravine method worked well and sparked numerous heuristics for selecting its parameters and improving its behavior. Our view is convergence was never proved. It inspired polyaxivable method, which seems to have inspired Nesterov accelerated gradient method. It was in 2021. So in this lecture, our ambition is to answer these questions. Okay, we are going to give answers to these questions. And in fact, most important, we are going to go beyond this method and propose new improved methods. So this is the content of a lecture. It's a 2 hours lecture. So it's a 2 hours lecture, which is condensed to 30 minutes. After this general introduction of the Ravine method, we shall explain the link with the Nesterov, classical Nesterov accelerated gradient method. Then we shall give a dynamical interpretation of these two methods. And from this, we will obtain a convergence rate of the two methods. And after this comparison, this is a current research. We see how to improve the Ravine method, how to improve the Nesterov method. And we shall finish with perspective open question. The results I'm going to give today are new. They are not still published. You see, we plan to have archive paper within a few days. We rely on these papers. I have no time to comment on them. These are very recent papers, and I shall comment during the lecture on these papers. Right, so what's the link with Nesterov accelerated gradient method? I briefly recall it, the Nesterov method. Here we are in a Hilbert space, a convex differentiable function. We assume that the gradient is L Lipschitz continuous, the solution set is non-empty. You are interested in minimizing F. So Nesterov method is this. You see, you have first extrapolation and then a gradient step. And as I said, the important point is the tuning of the extrapolation. See, in order to have a fast method, the idea is to have extrapolation goes to 1 in a very controlled way from below and like 1 minus alpha over k. Okay, so if alpha is greater than 3, you have this order of convergence. And if alpha is strictly greater than 3, you can improve it a little bit, this order, passing from capital O to small o, and moreover, you have a convergence of H rates. These are recent results with Pepouquet and Chambol and Dossal. Right, here is the geometric view of the Nesterov method, extrapolation, and then a gradient method. See, the picture is quite different from Ravine method. In the Ravine method, you have 2 gradient steps and then extrapolation. Here is 1 extrapolation and 1 gradient. So the 2 methods, in fact, as you can guess, are very closely related. Here we write the 2 methods, you see, for Nesterov accelerated gradient is NAG, and Ravine accelerated gradient is RAG. Alpha is the parameter, which appears in the extrapolation coefficient. For Nesterov, I use the variable YK. And for RAG, for Nesterov, I use the variable XK. I consider this algorithm as generating sequences, the sequence XK. See, you have XK is K minus 1, extrapolation, YK, and then a gradient step. And for RAG, the sequence which is generated by I write it YK. You see, otherwise there is a lot of confusion in the literature. There are a lot of confusion. People, they say they work with Nesterov method instead of, in fact, they work with RAG and conversely. So the 2 methods are so closely, at least formally related, that you have to be very careful about notation and not to make confusion. Okay, so in fact the two methods, they come within the same equation. So in both method you have extrapolation and gradient step. The point is that the order is not the same. In Nesterov, you first do extrapolation and then gradient. In RAG, you first do gradient steps and then extrapolation. So the order is reversed, you see. They come within the same equation, but in a reversed way. And most confusing is the fact that if you're interested with Nesterov, okay, and you consider the sequence xk, if instead of considering the sequence xk, you consider the sequence yk, okay, then the sequence yk follows the Ravine method. So you see, within the same algorithm, you can generate two algorithms, depending on whether you consider the sequence xk or the sequence yk. That was the origin of confusion. It's natural confusion because it's life. So this is a formulation of this result. If xk follows Nesterov method, then yk follows the Ravine method. And conversely, if yk follows the Ravine method, then xk follows the gradient method. Just be careful that here, in order to have this equivalence, here you have to change a little bit, you see the extrapolation. Here it's 1 minus alpha of k and 1 minus alpha of k plus 1. Okay, this is a technical point, but if you want to be precise, don't forget. And the proof is completely, it's just some elementary algebraic operation, so I don't comment too much on that. So let's come to the basic question. Are these two algorithms the same algorithms? Okay, right. A way to answer this question is to look to the dynamical interpretation of the algorithm. That is to say, you are looking for a continuous differential equation which reflects, whose trajectory reflects the behavior of the iterates of the algorithm. If you do low resolution, I'm going to explain in a moment what I mean by low resolution and high resolution. If you do the low resolution of the two methods, you end up with the same dynamic, which is the well-known Boyd and Candace dynamic, which appeared in NIPS in 2014. And if you want to be precise, you say, okay, so they are more or less the same. If you want to be precise and really go into the detail and perform high resolution ODE, EDO is a French spelling for équation différentielle ordinaire. In English, ODE is ordinary differential equation. So sorry for that. High resolution ODE gives the same dynamics for the two methods. In fact, when we do the high resolution ODE of Nesterov and Ravine, you make appear an additional term, which is the damping governed by deviation. See, if you forget about this term, you have the Boyd-Candace plus some correcting term, but this is not really significant. What's very important is you make appear deviation in both, and this is the same equation. So a high resolution of the two methods give the same dynamics. And let me explain what the high resolution is. It's a very interesting concept when you are interested in the connection between algorithms and dynamical systems. It's a concept which comes from fluid mechanics. So here is the Ravine method. Okay, so replace WK by this expression in order to have an equation involving only YK, and then you elementary algebraic transformation. You obtain this form of Ravine method, which looks like, you see, the continuous dynamic. Here is the discrete version of acceleration of a velocity. And you see, because of this term, WK minus 1, you make appear the difference of a gradient, you see? And here you see difference of a gradient. Okay, there is deviation. You see, divide by H, and this is the discrete form of deviation. So when you pass to the limit, passing to the limit, that's you have the ansatz that YK is capital Y of TK, where TK is KH for some smooth curve. Then you replace YK by capital Y of TK, and you do Taylor expansion. In the classical, in the low resolution ODE, what you make Taylor expansion, and you just retain the term of order 0. That is to say, you let H go to 0. But doing so, you lose information. So the idea is not to let H go to 0, but to keep here the term of order H. That is to say, after the Taylor expansion, you neglect the term of order H2, which are very small because H is small, but you keep the term of order H. And if you do that, you obtain the equation which is written here, right? And if you do the same thing for von Nesterov, and that's the very surprising fact, you see, for Nesterov, okay, when you write the equation with only xk, okay, that's the Nesterov. Okay, you have the acceleration, here's the gradient, okay, the gradient of f at yk. Yk is here, right? And here is deviation. That's a very surprising point. For us, it was very, very surprising. We didn't imagine that deviation was present in the Nesterov algorithm, because here deviation is present in the implicit form. Because when you do Taylor expansion of this is small, you see, this is okay, this goes to 0. When you do Taylor expansion, you make appear deviation. So when you do high resolution ODE of the Nesterov method, that's what appears, you see. But the difference between Ravine and Nesterov is that in the Ravine method, deviation appears in explicit form, and in the Nesterov algorithm, deviation appears in the implicit form. That's a basic point, and this has important consequences if you want to go further. Right, concerning the rate of convergence, still 10 minutes, isn't it?
Yes, I mean, in principle, what do we say? So you have time until, yeah, 10 minutes would be definitely fine, sure.
Okay. So let's talk about the convergence rate. That is important, I think, it's the convergence algorithm. And this is recent result obtained by Su, Du, Jordan, and Shi, Du, Jordan, and Su, and the paper with Favili, not published. You have the same convergence property for the two methods. But the very important point, you see, completely new, this was discovered, you see, for the Ravine method, this was recently discovered by Jordan and his co-authors for that programming. We discovered that the same property is true for Nesterov. This came as a big surprise, you see, we didn't imagine this to be true. And okay, and it's true. And the reason, you see, the reason for that, why people didn't mention that in the earlier paper, see, when you do the Lyapunov for Ravine, but it's the same thing for Nesterov, you write the equation, okay, in a Hamiltonian form, you have a classical Lyapunov analysis, and the point is that you have to use the gradient inequality in a sharp form. Here, you have to use the gradient inequality in the case of a convex function. In the case of a convex function, you have this additional term which involves the difference of a gradient. And this is essential, you see, in order to obtain this term here. If you don't use this term, this sharp form of a gradient descent lemma, you miss this term. And this is what happened in the classical earlier proof. So if you do this sharp Lyapunov analysis, you have this term which appears, you see, so if LS is strictly less than 1, this is non-negative, alpha greater than 3, this is non-negative, so AK is decreasing, and when you do summation of this inequality, you obtain this estimation. All right, and you can see for Ravine and elementary inequality, so you have it for Nesterov. But you can do exactly the same Lyapunov analysis for Nesterov. So we have two proofs of the result. We are so surprised by the result that we gave two proofs of it in order really to be sure that there was no mistake. So now the question is, can we improve these methods? Right, and at this point, this is one of my favorite topics of 1.2, which is a connection between continuous dynamical system and algorithms, which is a very, very difficult topic with many surprises. And first, from 10 years ago, we have been working on this dynamical system. We are convinced that this dynamical system plays an essential role in mechanics, in optimization, in many different domains. And this continuous dynamic exhibits good attenuation of oscillation. Oscillation really plays a fundamental role. But the problem is that this property is less obvious for the associated RAG algorithm. You see, when you do high resolution ODE of the Ravine method, we obtain this dynamical system. But we have not the same nice property for the algorithm as for the continuous dynamical system. So how to explain this? In fact, the Ravine method follows from the explicit discretization of this dynamic. When you pass from this dynamic to the Ravine method, you just do explicit discretization. And explicit discretization doesn't preserve all the good property of a continuous dynamic. This is a Toulouse approximation. How to remedy? The idea is to go first through implicit proximal discretization. Implicit discretization preserves the property of a continuous dynamic, but numerically the prox can be difficult to calculate. So the idea is to do the implicit discretization first, then replace the prox with a gradient step. So doing, you preserve a good structure of the algorithm, and if you take S small enough, you preserve a good property of the dynamic. So that's a program we are going to develop in a minute. You see, explicit discretization give right. We are going to obtain a better algorithm by following this device. In order, I think this is something important. You see, just illustrate this in a simpler situation. Take the Suboid-Candace dynamic, which is here. If you do implicit discretization, okay, you obtain the prox gradient, the proximal, inertial proximal algorithm. This is just one line computation. Then you replace the prox by a gradient step and you obtain S12. So you see, if you start from this dynamic and you follow this scheme, you obtain a very good algorithm, which is S12. By contrast, if you do explicit discretization, you obtain the heavy ball method. And you know that the heavy ball method is not so good for general convex function. Right, so in this case, our scheme works well. So follow it in the case of this Hessian damping, explicit Hessian damping dynamic. So we first do implicit discretization here. Okay, we take xk plus 1 here. You can imagine other variants more implicit, but the important point is here. So if you solve with respect to xk plus 1, you obtain this proximal formulation. So you replace the prox by a gradient step. So you call this yk, and then you compute a gradient step at yk. And that's a new algorithm. That's the algorithm we introduced in the paper with Bani, Fadili, and Riyai. And for this algorithm, okay, we obtain the same nice theoretical convergence property. So this property, all these algorithms, they have this nice property. But from a numerical point of view, there is a big difference because this algorithm do preserve really the nice damping property of the continuous dynamic. We illustrate this in the case of lasso problem. So lasso problem is not a smooth problem, but you can reduce to a smooth function. It's a classical trick. You use the metric which is associated to the linear operator A, and you work with the Moreau envelope of F with respect to M. You preserve the solution of your problem, and so doing you have a function which is C1, and such that the gradient is precisely the operator you are interested with, which is a splitted operator. Right, and so you write the algorithm, so you have all these nice property you see with this fast convergence of the gradient, and now you see that the the numerical properties of the algorithm are far better. Here in red is the FISTA method, which corresponds to a Nesterov method. And in blue is the method which is obtained by the algorithm IGAHD. And in black is the predicted 1/k² rate. This is for less so problem with the L1 norm regularization. With a group lasso, you have exactly the same type of picture. You see the oscillation are far less, and we have better convergence rate. Here the same, you see, you have a lot of oscillation with FISTA, and here you have, after you see here we are 10 minus 10. So it's very, very, very small, you see. So what appears here is not really significant. You see here you have really a reduction of the oscillation, and for nuclear no. And I have just a couple of minutes to talk about the last direction of research. So how to improve the Nesterov method. Here we improve the RAG method. And to improve Nesterov method, in fact, as I said, Nesterov is naturally related to implicit form of variation. When you write the continuous, when you pass to the continuous form of a Nesterov method, you see that variation appears through the implicit form. So this is the, I think, in my opinion, this is the dynamic which is naturally linked to Nesterov. If you forget about this term, you have suboicandesce. I think that this form is right. That's what we call the implicitation. Implicitation, because if you do Taylor expansion of this, x dot goes to 0, so you obtain exactly this form. And you have, this is the work of Adesca, Laszlo, and Pinta. You have also the same type of convergence, fast convergence of the gradient. And what we discovered is that this system here, you can rewrite it as a first order system in time and space. You see here are only first derivative, and here there is no moration, you see gradient. And this system is very interesting because you can extend it to the non-smooth case, and you can, so doing, you can also develop proximal gradient method, but here I just talk about gradient method. So you have this system, and we are going to apply our device to this system. So we just do implicit discretization. So it's a system, you see the variable here is y. Okay. The gradient enters via y. So implicit discretization, yk plus 1. You solve with respect to yk plus 1, you have the prox here. You replace the prox by a gradient step, and you obtain this algorithm. You can rewrite this algorithm. In fact, just do some algebraic computation. You can write this algorithm as a relaxed inertial proximal algorithm. And you end up with this recently discovered by Minge-Labarre. Okay, our presentation is new. You see, Minge-Labarre say, okay, this is the good algorithm. Okay, but if you want to understand why it's a good algorithm, it's not clear. You see, since the proof, the weak point of a paper is that the proof is awful. You see, I tried twice or thrice to read the proof, but I failed. I know one person who read completely the proof. It's the evaluator, a reviewer of the paper, and he told me, okay, the paper is okay. It has been published, but the proof is awful. And at least we have succeeded introducing this algorithm in a smooth way. But now it's a very interesting job to have a simpler proof of the algorithm. And this algorithm, in fact, do behave well. At least the numerical is very good. You have fast convergence of values and gradient. This algorithm has a similar structure. You see, if you forget about this term, it's the structure of Nesterov algorithm. The difference here is that you have two differences. You have a relaxation term, which is here, and you have also a coefficient beta in front here. Yet you see the relaxation compensate the fact that this may be large. And the relaxation, you see, is connected with relaxed inertial forward forward-backward algorithm introduced Cabot, but the difference here is that the relation is taken at xk. That's important. In the paper with Cabot, we take the relation at zk, and here it's xk. And they did extended their algorithm, as I say, to non-smooth and proximal gradient algorithm. This is something which must be confirmed. So I have no more time, and we can return on this question. And here, if you have a question, you see, you can pick up question a lot for many years, work for many years. Okay, so thank you very much.
Thank you, Hedy, for this wonderful overview talk. I didn't want to stop it so abruptly, so you could have also give a bit more time for your talk, but it's a very fascinating overview that you give here and many new possible directions. So I think, yeah, we can start the discussion. So please, if you have questions, feel free to unmute yourself and ask questions or put them into the chat. I can read them out loud. So Jérôme is also thanking you for the talk. So maybe I have a question to start with. So this higher resolution ODE that you used at the beginning to motivate the algorithm, so what exactly would it mean to have a high resolution ODE? Can you explain this term maybe a little bit?
Okay,
what it means?
It's a concept which is classical in fluid mechanics, you see. In fluid mechanics, you have large structure and you have small structure, you see. And if you want to take account of the small structure, you have to do you have to use different scale. You see, the idea is to have to describe a physical model with different scale. You have adapted to large, huge phenomena, just like in the atmosphere, and you have a scale which is adapted to description of small local phenomena, you see. So it's the idea of a different scale. And here you have different scale. You have H, H2, and H3, and so on. So you do tailored expansion, and depending on the order of the development, you have a more precise, you see, description of your phenomena. Hi, Jérôme.
I see.
Thanks, Hedy. It was very interesting. I have a question for the specialist of PDs that you are as well. Are you aware of physical systems that would be governed by this type of dynamics, or are these just machines that we are building to optimize? Do you think we can find in nature this type of dynamics? Or
you're right. This is a very interesting, and the answer, okay, is not so simple. You see, in fact, the reason why I've been so interested with this dynamical system is because of a physical, mechanical interpretation. You see, when I use this dynamical system, I have mechanical intuition of the system. That's what made me very confident with them at the beginning. And mechanical intuition, you see, damping governed by variation, it's the same thing as in mechanics. You see, it's damping, it's a geometrical damping or strong damping for PDEs, which is governed by the Laplacian operator, you see. And in mechanics, it's well known that this strength damping has a very efficient effect on the stabilization of the oscillation. See, in mechanics, strong damping and mechanical stabilization of oscillation, you see, this type of dynamical system is very classical and very important, right? Second reason is that I've been very interested with shocks, you see, damped shocks in mechanics. And this type of dynamical system is fantastic. You have, within a single equation, you can describe phenomena which are very complex, you see, the crash, you see. But the point here is that you can modelize only completely damped shocks, okay? In fact, you have to go through more sophisticated model in order to introduce shocks with, I don't remember the name, you see, where you interpolate between elastic shocks and non-elastic shocks. Coefficient E of, I don't remember the mechanical term, but okay, you can modelize the shocks with this, and you are familiar, we are familiar with that, you see. So these are, and more important, you see, I think that there is something very interesting to do concerning a marginal geometrical damping deviation, you see. In the Polyakov ball for strongly convex function, the optimal coefficient corresponds to the square root of coefficient of strong convexity of a function. So I have the intuition that in fact the right operator is not the deviation, but the square root of deviation. See, you have to go through fractional powers of subdifferential of convex functions. I think that would be a very interesting direction of research, you see. I think that deviation is not the ultimate point of this type of things. For example, when you have the Laplacian, when you have PDEs, you make damping governed by the Laplacian. In fact, people, they usually use a fractional power of a Laplacian, okay? And these have real physical and numerical interest, you see, for the damping of oscillation. And I have the intuition that for optimization, there is something to do in this direction.
In principle, we're out of time, but Radu also has a question. So maybe Radu, if you quickly.
Yes, short question. So thank you very much. Thank you, Hedy, for a beautiful talk. So we are noticing this, this month, these weeks, a very interesting development. So two of the, let's say, most important concepts in optimization, like the full splitting methods by ADMM, Shambol-Pock, and the nested of methods are brought together. So that there is a mixture of nested of ideas in the context of primal dual algorithms, where one has to update primal and dual variables in the nested of way. But there are still many open questions. I mean, so we are not so far to have all the results we want to have. There are improved rates for primal dual gaps for objective function values. I mean, in the continuous time case, I guess these ideas work better than in the discrete time. So just combining Nesterov with, let's say, ADMM techniques. So what do you think? So using the Ravine's method instead of Nesterov in this context, would this have a benefit?
Yeah, for sure.
I mean,
it's free. You see, it's
okay.
Free. You can Ravine, or you see there are many different algorithms in this lecture. So the idea is deviation. You see, deviation damping. When you have inertial system, introduce deviation in a suitable form, deviation damping, and you have a better algorithm. You damp the oscillation, and you keep the convergence rate.
Great, thank you.
Thanks. Cora, you also raised your hand.
Hello, thank you very much for your talk. I'm sorry, I don't want to take much time. I just want to ask you that about the so I saw in your picture for the algorithm that it has a better asymptotic rate. So in your plot of numerical results, it seems very much that the asymptotic rate is much better. So, but the worst case complexity analysis does not capture this. The worst case complexity analysis just gives you a global bound. So my question is, could you provide maybe a complexity analysis that maybe studies the algorithm on phases, the first phase and then the asymptotic phase, And then maybe what you observe numerically could also be captured theoretically.
Oh yeah, you're right. You're right. In fact, you see, we don't know if this very favorable behavior does depend on the particular example we consider.
Yeah.
You see, it's something general. We don't know. You see, it's a question. It's this deserves further studies, clearly.
Okay, but we've seen in other analyses that sometimes when you can do this kind of phase analysis, you know, if you have some behavior in phase 1, some behavior in phase 2, maybe this would allow you to capture this improved behavior here, because for these methods, you know, the worst case is always going to be essentially the same.
Yeah, you're right. You're right.
Thank you.
Thanks.
Very good question. Yes, thanks. All right. Thanks again. In principle, we should continue with the schedule, although you realize probably that I would not like to make this such a straitjacket of events. But let's thank Hedy Attouch for this wonderful talk once again. So I'm just applauding like this. Thank you very much. So our next speaker, according to the schedule, is Professor Mark Thibault. So I'm kindly asking Hedy to stop sharing screen now. And Mark, you can launch your slides, please.